Okay, our next problem will be significantly more difficult, but we'll use the same technique. Y double prime plus the quantity 1 plus x squared times y equals 0. Notice while the equation is still homogeneous, it is nonlinear because it has this variable coefficient. And that's really going to allow the technique we're looking at now to shine. Okay, our substitution is going to be y equals the summation m equals 0 to infinity of a m x to the m. We'll expand out the first few terms just so we can resolve its derivatives and basically build what is a more complex differential equation. This will produce a naught plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth plus a5x to the fifth, and on and on. And now we'll need the first derivative of this just so we can find the second derivative, but we don't really need to do much with this first derivative line. So I'm going to write it, and then I'm going to actually remove it. So y prime is going to be equal to a naught. Oh, a naught goes away. It's a1 plus 2a2x plus 3a3x squared plus 4a4x cubed plus 5a5x to the fourth plus 6a6x to the fifth, and on and on. Now, I really only wrote down the first derivative just so I can form the second derivative, but then I'm going to erase this because we don't really need that line. We're trying to build this function, so I'm actually going to insert in between x squared times the y function so that we can build that, but let's get the next derivative. So y double prime will then be the first derivative of this guy. And I'm going to try and line things up, although I won't really do a good job of that. It's not important because now that we know we're lining up coefficients of like polynomial terms, it's pretty easy to pick those out. So the next derivative is going to be 2a2 plus 6a3x plus 12a4x squared plus 20a5x cubed plus 30a6x to the fourth, and on. Now what I'm going to do is go in and remove that first derivative line, which we didn't need anyway. We were just building it to build the second derivative. And instead I'm going to fill that space in with something useful. I'm going to fill in x squared times the entire line y, because that will replicate the third term of the differential equation, the first term being y double prime, the next term being the line y itself, and the third term, or the third line being x squared times y. So let's build in x squared y, and of course that's going to be this entire line with all the x powers increased by 2. So it's going to be a naught x squared plus a1 x cubed plus a2 x to the fourth plus a3 x to the fifth plus a4 x to the sixth plus a5 x to the seventh. Okay, and now we can start building our coefficient relationships. And of course we'll start at x0, and that produces the equation a naught plus 2a2. There is no x0 in the x squared y, so I'm summing these three lines, which represent the three terms in the differential equation, and setting them equal to 0. So it's just that, it's 2a2 plus a naught. And that produces the relationship that a2 is equal to negative 1/2 of a naught. It's important to note that it skips an order. I fully expect this to do that in every single term, that I'll never get a2 in relation to anything other than an even term, and I'll never get A1 in relationship to anything other than an odd term, because this one appears to skip orders. And it's that multiplication by x squared that's causing it. Okay, our next line is going to be x to the first, so we'll find those in all three. Again, x to the first is 6a3. X to the first is a1. And again, the x squared y doesn't feature that. So that tells me that 6a3 is equal to, a3 is equal to negative 1/6 a1. So there it is, a2 in terms of a0, a3 in terms of a1. I imagine now we're going to find a4 in terms of a2, which will be a0, and a5 in terms of a3, which will be a1. So let's find those inevitable terms, x squared. And the x squared is going to be 12a4 plus a2. And then finally, the middle line comes into play at the x squared line for the first time, plus a0 equals 0. So that tells me that 12a4 is equal to negative a2 minus a0. But a2 itself was negative 1/2 a0. So that means this is positive 1/2 a0 minus a0. That's negative 1/2 a0. So I just substituted the a2 value in here and then resolved it to entirely be in terms of a0. That means that a4 is actually equal to negative 1/24 of a0. And one more line, x3. The x cubed produces 20a5 plus a3 plus a1. And once again, 20a5 is equal to negative a3 minus a1. a3 right here is given in terms of a1, it's negative 1/6. So that makes this plus 1/6 a1 minus a1. That's going to be negative 5/6 a1. Negative 5/6 a1. And that means that a5 is actually equal to 1/24 of a1. Okay, we have the first 5 coefficients. We can go ahead and build our new y. So y is equal to a0 plus a1x plus a2 is really negative 1/2 a0, so it's minus 1/2 a0 x squared. a3 is really negative 1/6 a0, so it's minus 1/6 a1 times x cubed. a4 is really negative 1/24 a0, so the next term is negative 1/24 a0 x to the 4th. And the next term, a5th is negative 1/24 of a1 times x to the 5th. And it goes on and on. We can see it alternates between a1 and a0, so I'm going to factor those two. I'm going to factor out first a0, and what's left behind is 1 minus x squared over 2 minus x to the 4th over 24, and that one continues, plus a1 times the quantity, x minus 1/6, minus x cubed over 6, minus x to the 5th over 24, and that one goes on. Unfortunately, unlike our last example, these are not Maclaurin series of recognizable functions, so this represents the simplest representation of the final series solution.